Welcome to the study of electrostatics or static electricity. Okay, we're making our first foray into what would be a second semester physics course. Okay, you just completed mechanics, and now we're going to go into the basics of electricity and later on in the semester magnetism. If you take a look at the screen, okay, you'll see a few terms that I want to familiarize yourself with and connect you also with some of the previous knowledge that you have about the subject. So let's take a closer look. Scientists have known for a long time, okay, that there have been two types of charges. This goes back hundreds of years. Over the centuries, we've given those two types of charges different names. Okay, we finally settled on Benjamin Franklin's designation of calling one kind of charge positive and the other negative, and that works pretty well because we can use math a lot of times to help us deal with large numbers of charges. At any rate, we get to the fundamental law of charge, okay, which is that likes repel and opposites attract. I think you come into the class knowing that already. Okay, things like protons carry positive charge and electrons carry negative charge. So electrons repel each other, protons repel each other. All right, another thing you want to know about charge is charge conservation. Okay, just like energy or mass, it's neither created nor destroyed, simply transferred from one system to another. Okay, so when something loses charge, right, that means that charge went somewhere else. Okay, the next term, ion, you probably are familiar with that from chemistry. Okay, an ion is, for example, here's the simplest atom, which would be a hydrogen atom, right? It has one proton in the nucleus, and although this is a rough model, right, there's an electron on the outside and it has a negative charge. So when hydrogen becomes ionized, right, it loses that electron and gains a charge of 1. It's now just the charge of the proton, okay, which is right here, is a charge of 1. It's lost the electron. Okay, now a key thing that I'm going to hammer home repeatedly is that the way something becomes charged is by electrons moving. Okay, electrons are on the outside of the atom, okay, and they're the ones that are easily removed. So if something becomes positively charged, it does not gain protons, okay? The way it does that is it loses electrons. Remember that all objects, okay, if this is our object here, all objects tend to be neutral, right? But neutral means no charge, right? No positive or negative charge, but doesn't mean no charges at all, right? Remember that every object is made up of billions and billions of atoms, and billions of atoms have billions and billions of protons with billions and billions of electrons. It just so happens that there's equal numbers of each, and so the net charge, right? The net charge of most objects is 0, okay, or neutral. All right. So for this object to become positively charged, it doesn't gain protons, okay? That doesn't happen. It loses electrons, right? Leaving exposed protons behind. Okay, the other thing that you want to know about are different types of materials, okay, and how they behave electrically. Okay, we have two basic types. We have conductors and insulators. Okay, conductors, typically a metal, are materials where the electrons are loosely bound and they can move freely. Okay, so for example, on a conducting sphere, right? So here's a conducting sphere. It's metal. All right, if you dump some electrons on there, right, maybe you charge a rod up, okay, with cloth, and you have some electrons on there, and then you touch it, and the electrons go into the sphere. Those electrons are actually immediately going to move freely, okay, and they're going to spread around to the outside of the sphere, because on the outside of the sphere is where there's the most space, and electrons hate each other, right, likes repel. So those electrons will immediately spread around to the outside of the sphere, and they can do that because metals allow electrons to move freely, okay. Insulators, okay, like plastic and rubber, doesn't happen that way. If you charge this rubber rod here, okay, by rubbing a cloth on it, you might get some negatives right there, okay. You might transfer some electrons from the cloth to the rod, but those electrons, they're going to stay right there, okay. They're not going to move around. But if it were a metal rod, right, those electrons would immediately spread out as evenly as possible all over the metal rod. Okay, and again, that's because of how the electrons are bound bonds-wise, okay, at the atomic level. Let's take a closer look at how we might charge an object. Okay, there's two basic ways. One is charging by conduction. Okay, and I'm going to use an object here called a It's basically just a conducting sphere, okay? So this circle here is metal, all right? And it's also called a proof plane. But that's kind of an old-fashioned term. I don't think you're going to hear that too much. Just a conducting sphere is fine. But that's metal, okay? And it's this is going to have to be an insulated base, right? So this would be an insulator like a wood or rubber, okay? Something like that. That way the charge can stay on the metal sphere. Remember that this metal sphere is made up of many positives and many negatives, right? Billions and billions of protons, billions and billions of electrons, and it starts off neutral, okay, like that. Now, I'm not going to draw those in there after this time. I'm just going to leave it blank. If you see an object that's just empty on the inside, we're going to assume that it's neutrally charged, okay, which is not charged at all. Now, what we want to do is we want to make this conducting sphere have a net charge on it, right? Either be positive or negative. In order to do this charging by conduction, you're going to need an object that's charged a certain way, okay? So let's acquire a rod, okay? So we've got a rod here, and let's say we rub it with some cloth and it becomes negatively charged. It's got some negatives on it, okay? Probably didn't draw that too well. I should probably clump them up a little bit. To charge by conduction means to charge by direct contact. So all you're going to do is take that rod, touch it, okay, and those negatives will go on to here, right, by direct contact, and then as discussed before, they will spread out evenly and you'll end up with a negatively charged sphere. So when you charge by conduction, the object that you charge ends up having the same charge as the object that you charged it with, right? The rod and the sphere have the same charge. There is another way to charge an object, and that is called by induction. Okay, we're going to use a twin leaf electroscope. Okay, that's what you see here. Here are the twin leaves hanging down, usually like an aluminum foil, and we're going to charge this by induction. Okay, so right now it's neutral, right? It has a charge of 0. I'm going to bring again a charged rod. Okay, I'm going to bring a charged rod close. And this time, let's say it's positive, okay? It's a positively charged rod. That means it lost electrons, right? Now, when you bring it close to this metal sphere here, okay, I'm going to draw this a little bit larger. This sphere starts to look like this, okay? The electrons on this sphere begin to be attracted to the positive charge of the rod, okay? And remember that on a metal sphere, the electrons move freely, okay? So notice that the sphere is still neutral, right? But now the charges have separated. Okay, it's polarized. All right, we've polarized the sphere. Now, while the sphere is polarized here, okay, we are going to ground the sphere, right? So the rod's still here, it's positively charged. And now with our finger, right, coming from the opposite side, okay, we're going to ground the sphere. And what that's going to do is, right here, it's going to actually dump electrons, okay, onto this positive end of the sphere, right? Electrons from the ground are going to jump up onto the sphere. And then you take both things away, your finger and the rod, and what you're left with, right, is you're left with a negatively charged sphere, okay, which then they spread out all over the electroscope, and then those twin leaves separate. Why do they separate? Well, because the like charges spread out evenly all over the metal surface, and they make both of those leaves be negatively charged, and like charges repel. So the leaves are hanging here, not charged yet. At this point here, they become charged, okay, when they acquire the negative charge from the Earth. All right, let's talk about grounding, okay, the process of grounding an object. When you ground an object, it returns to neutral. Okay, you see here the electrical symbol for ground right there, which is to return it to the neutral state, okay? And the way grounding works is it connects to the ground or the Earth, okay? And the Earth is a donator or acceptor of electrons. Earth is the largest object around, so it will easily donate or accept a few electrons. Electrons love to go into the ground because there's more space on Earth than any other object, because Earth's the biggest object around, and so electrons have more space on Earth than anywhere else, and therefore they always prefer it because they hate each other so much. They always want to get away from each other. All right, just a few more things to wrap up electrostatics here. Let's go to the next page. Okay, polarization, we've talked about that already. I mentioned it briefly, but if you start with a conducting sphere, okay, that's neutral, okay, and then you bring a charged object close to it, right, like a rod, okay, a charged rod here, like so, and we'll charge this rod positive, okay, like in the previous example. What that's going to do is that's going to move this situation here, right, neutral and evenly spread out. That's going to change it into this situation here, okay. The overall charge is still neutral, but the charge is separated, okay. And that's what happens when you rub a balloon, right. You saw this in the simulation perhaps. If you rub a balloon on your hair, it becomes negatively charged, right. How does it stick to a neutral wall, right? Well, that's because it drives the electrons in the wall back, okay, and it leaves these positives exposed up here, and then you have a little positive negative attraction. But notice that the wall remains neutral, okay, and this is balloon is negative. So that's polarization. We can also talk about sparks. You may have seen this in the lab, in the classroom, but right here, okay, in this situation right here, sometimes when you bring a charged object close, you actually hear a little sparking, okay. And spark is simply the sound of charge transfer, okay, electrons moving through the air. And a spark is basically a mini bolt of lightning, okay, and the sound that goes with it is like a mini bolt or a mini sound of thunder, okay, a mini thunder strike. All right, you can think of sparks that way. And then finally, we do have some charge generating devices. These are, for the most part, kind of antiquated. Okay, I'm not really going to hold you responsible for that. But at the end of the notes, you see a few things, the Leyden jar, the electrophorus. You should have a rough idea of how those work, okay, by reading through the notes. The main thing is you should know about a twin leaf electroscope, okay, which is what we used in class.